Right now, pretty much every tech company on Earth wants the exact same thing.
Oh, for sure.
Like, if you've been paying any attention at all to the generative AI space, you know the holy grail isn't just, a chatbot that can write a decent poem anymore.
Right, we're way past that.
Yeah, we want AI models to act as independent agents.
Yeah.
The dream is to hand a model a really complex prompt, take a step back, and just watch it browse the web, write its own Python code, execute it, and, I don't know, solve multi-step math problems entirely on its own.
Which is a huge leap.
It is. But there's this kind of dirty secret behind teaching them to actually do this multi-step reasoning. Because if you look at the compute budgets and the engineering hours required to train these agents today, the process is, well, it's incredibly slow, insanely expensive, or just deeply, deeply flawed.
Yeah, I mean, it's an absolute logistical nightmare for researchers right now.
Really?
Oh, absolutely. Because when you're training an agent, you're no longer just grading a single output like a paragraph of text. You are evaluating this massive chain of discrete decisions.
Right, step by step.
Exactly. So if you have an AI that takes, say, 15 distinct steps using 3 different tools to solve a problem, and it gets it wrong on step 14, the challenge is figuring out how to teach it where it went off the rails.
Which sounds impossible.
It's incredibly hard. Doing that in real time without spending just an absolute fortune simulating every possible alternate reality on a live server is, it's one of the hardest problems in machine learning today.
Okay, let's unpack this because that brings us to the actual mission of today's deep dive. We are looking at a brand new, state-of-the-art generative AI paper from Microsoft Research in the University of Amsterdam.
It's a really fascinating paper.
It really is. It introduces a method that honestly looks like a massive shortcut for training these AI agents.
Yeah.
It's called REOPD, which stands for Replayed Prefix on Policy Distillation.
Way mouthful.
Yeah, but by the end of this conversation, you'll understand how this new method takes that incredibly expensive, time-consuming process of live agent training and converts it into a highly reusable offline resource.
Which is the key.
Right. They're claiming they can make agent training at least 4 times faster, drop live tool calls to absolute zero, and surprisingly, actually make the resulting AI smarter than it would be using previous live methods.
Which is a bold claim, frankly. To get higher performance while explicitly restricting the model from interacting with a live environment goes against, well, a lot of conventional wisdom in how we train reinforcement learning agents.
Totally. So to really grasp why REOPD is such a breakthrough, we have to look at the frustrating trade-offs the researchers who build these systems are currently stuck with.
Yeah, it's basically a two-camp problem right now.
Exactly. If you're trying to train an agent today, you basically have to choose between reinforcement learning or knowledge distillation.
Let's look at reinforcement learning, or RL, first.
Look.
So RL is essentially learning by doing. It's an on-policy method, which means the model is generating its own actions, stumbling into its own unique mistakes, and trying to recover from them.
Trial and error, basically.
Right, pure trial and error. But the glaring issue with RL in these really complex multi-turn environments is that the feedback is incredibly sparse.
Wait, when you say sparse, we're talking about the actual mathematical reward the model gets, right?
Yeah, exactly. Just consider what a scalar reward actually looks like to a neural network.
Right.
The AI generates, say, 1,000 tokens of thought. It decides to use a calculator tool. It parses the output. And at the very end of this massive sequence, it gets a simple 1 for a correct final answer, or a 0 for incorrect.
Oh, wow. So just a binary pass or fail after all that work.
Yes, and that single digit is supposed to update millions of weights across the network. It gives almost no granular information per token about what specific microdecision led to the success or failure.
That seems really inefficient.
It is tremendously sample inefficient. You have to run millions of iterations before the model statistically intuits the specific mechanics of its own success.
Got it. So to fix that sparse feedback loop, researchers pivot to the second camp, which is knowledge distillation.
Right, the learning by watching approach.
Yeah, exactly. You take a massive, highly capable teacher model, maybe like a 30 billion parameter system, and you have a smaller student model observe it. And the feedback here is dense, not sparse.
Very dense.
The teacher is handing over its exact probabilities, its logits, for every single word or action at every microstep. But the catch is that standard knowledge distillation is off policy.
Right, which means the student is only learning from the teacher's perfect golden examples. It never actually sees the messy reality of failure.
For those of you listening who are gamers, it's kind of like trying to learn a highly competitive video game by only watching a Twitch streamer's highlight reel.
That is a perfect analogy.
Right, that's off-policy distillation. You see flawless, perfect gameplay, but you never see what happens when the player gets backed into a corner. Versus reinforcement learning, which is just you sitting in the dark mashing buttons until you accidentally win and the game says, good job, but you have no idea which button combo actually worked.
The Twitch highlight reel analogy is incredibly apt here, because the consequence of that off-policy distillation approach is disastrous when you deploy the student model in the real world.
How so?
Well, during inference, if the student model makes even a slight miscalculation early on in a multi-step task, it drifts into a state space it has never seen before.
Oh, because the streamer never made that mistake.
Exactly. The Twitch streamer never made that specific mistake, so there is no training data on how to recover. The errors just compound exponentially until the agent hallucinates completely and the task crashes.
But wait, hasn't the AI community already solved this? I feel like we've seen a lot of papers lately on policy distillation, or OPD, where the teacher coaches the student on the student's own gameplay.
Yes, the community absolutely uses OPD.
Right, where the student generates the path, makes a mistake, and the teacher steps in to say, okay, based on the mess you just made, here is the statistical probability of what I would do next.
And for single-turn text generation, like translating a block of text or drafting an email, it works brilliantly. The student stays in its own relevant distribution, and the teacher provides dense step-by-step corrections.
So what's the problem?
The entire system falls apart the moment you apply it to multi-turn agentic tasks.
Because agentic tasks require external tools. Searching Wikipedia, pinging a database, running a Python script, waiting for the output, and then planning the next move based on that specific output.
Which introduces just an absolute logistical nightmare for training.
I can imagine.
If you want to do OPD online for a multi-turn task, the student has to physically interact with the environment at every single step to generate its own on-policy history.
Oh, wow.
Yeah, it has to write the code, send it to a live execution server, and wait for the result. And then the teacher model has to be freshly queried on every single one of those resulting histories to grade the student's next proposed move.
The compute overhead for that must be staggering.
The paper lays out the exact numbers, and they're brutal. In their math environment, running online OPD required up to 15 live tool calls per single trajectory.
15.
Yes, and because of all that live interaction and waiting for servers to return results, it took 169 seconds just to complete one training step.
One step.
One step. When you scale that up to the millions of steps required to train a foundational agent, the time and money required are astronomical.
So you're burning 169 seconds per step, just sitting there waiting for a sandbox environment to execute Python, just so the teacher can evaluate the weird, novel path the student wandered down.
And honestly, the time and money aren't even the fatal flaw here.
Wait, really? What's worse than that?
The real issue is what the authors call the prefix trap. This is a fascinating two-sided distribution shift that happens when you force a teacher to grade a student's live environment interactions.
Let's break down this prefix trap, because if you're building multi-agent systems, this seems like the hurdle you're constantly hitting.
Right. So if you make the training entirely student on policy, meaning the student is totally steering the wheel and generating the history of actions, the situations are undeniably relevant to the student.
Right, you fix the Twitch streamer problem because the student is learning in its own messy environment.
Exactly. That's the student occupancy shift. But the student is a smaller, less capable model. It might steer into such weird, nonsensical, hallucinated situations that when you pause the training and ask the massive teacher model for the ideal next move, the teacher is completely lost.
So if the student agent completely hallucinates and drives the car into a ditch, the expert teacher gets so confused that its advice on how to get out of the ditch is actually garbage.
That's exactly it. Because the teacher model was never trained on how to get a car out of a ditch. It only knows how to drive flawlessly on the highway.
That makes a lot of sense.
So if you query the teacher in a bizarre, student-induced state, the target distribution it returns is no longer a trustworthy signal. It might just hallucinate right back at the student. So researchers are caught in this impossible tension. You desperately want histories that are relevant to the student so they learn to recover from errors. But if those histories are too relevant to the student's bad habits, the teacher's grading becomes completely useless.
This perfectly frames the problem OPD is trying to solve. Online OPD is too expensive, it takes 169 seconds a step, and it risks confusing the teacher anyway through the prefix trap. So what if we just, I don't know, turn off the live environment? The Microsoft researchers realized they could bypass the live servers entirely, right?
That is the core innovation of RioPD, replayed prefix on policy distillation. The first radical step they take is removing the live environment from the student's training loop completely. No Python execution servers, no live Wikipedia pinging.
Okay, but how do you train an AI agent to use external tools without actually letting it touch the tools?
By relying on an offline pool.
An offline pool.
Yeah, instead of letting the student run wild and generate its own environment responses, ROPD takes pre-recorded trajectories from the teacher model. And the beauty of this is that you get these recordings basically for free.
Because they already ran the teacher model through training.
Exactly. If the teacher model was previously trained using reinforcement learning methods like GRPO, which is widely used to train reasoning models right now, it naturally generated hundreds of thousands of recorded rollouts during its own training phase.
Oh, I see.
It already interacted with the live environment, it already ran the code, got the errors, and observed the outputs.
So you just save the log files. You build a massive database of the teacher's past actions and the environment's past observations.
Precisely. You take one of these teacher-recorded prefixes, which is just the history of past actions and tool outputs up to a specific step. You feed that exact history to the student, and you say, based on this specific situation, what is your next move?
Oh, that's clever.
The student proposes its own action for just that current step, and the teacher grades it based on its own internal probabilities for that same step.
Okay, here's where it gets really interesting. It's kind of like pausing a grandmaster's recorded chess match halfway through, turning to a novice student and asking, what's your move here?
Yes.
You don't need a real chessboard. You don't need an opponent to react. You just need the historical record of the game up to that exact turn.
And because it's a recorded replay, the live environment is never queried. The number of actual tool calls drops to absolute zero.
Which saves a ton of time.
Massive time. Because you aren't waiting for a live server, the training speed is completely transformed. Remember that 169 seconds per step in the complex math environment?
Right, the massive bottleneck we talked about.
It plummets to just 40 seconds. And in the slightly simpler search environment, it drops from 64 seconds per step down to just 7 seconds.
7 seconds. That is a staggering operational shortcut for anyone footing the cloud computing bill. You get the dense grading signal of the teacher without the massive overhead of the live environment.
It's huge for efficiency.
But I have to push back here on the logic for a second.
Yeah.
If they're only using the teacher's past recordings, the grandmaster's chess matches, aren't we just back to standard off-policy distillation? We're back to the Twitch streamer highlight reel.
I see where you're going with this.
If the student's just rolling along the teacher's perfect path, how does this solve the prefix trap? Won't the student still crash when it eventually gets into a real-world live environment and makes its first mistake?
This is where the engineering gets really, really clever. The researchers anticipated exactly that critique, which brings us to the secret sauce of the RioPD architecture, reliability-aware step decaying.
Reliability-aware step decaying. Walk us through how that prevents the student from crashing.
Okay, so the researchers acknowledge that the teacher's historical recording is only a surrogate for what the student would have done. It's an approximation. Right? Early on in a task, say step 1 or step 2, the teacher's path and the student's path are probably highly aligned. Both the grandmaster and the novice understand opening by moving the pawn to e4. So early in the trajectory, the teacher's history is a highly relevant low-shift surrogate for the student's own likely behavior.
Okay, so the early steps are safe because the divergence hasn't happened yet.
But as you move deeper and deeper into a multi-turn task, like step 10 or 15, the teacher's path looks increasingly alien compared to something the student would have naturally generated.
Oh, I get it. The grandmaster is orchestrating some complex knight sacrifice, and the student's just desperately trying not to lose their queen.
Exactly. The distribution shift between what the student would naturally do and the history it is currently being forced to learn from becomes massive.
So the Twitch highlight reel becomes completely unrelatable at the end of the video, so any lessons learned there won't stick for the student.
Right. And to solve this, the researchers introduced a mathematical weighting mechanism, basically a step-decaying sampling schedule. They use a hyperparameter called kappa, represented by the Greek letter, and they tune it to 0.6.
Why 0.6 specifically, and what is it actually doing to the training data?
It basically acts as an exponential decay weight on the loss function. A kappa of 0.6 essentially tells the training algorithm to heavily prioritize the student's decisions on steps 1, 2, and 3.
Ah, front-loading the learning.
Yes. It forces the model to pay strict attention to the early low-shift steps where the teacher and student are naturally aligned. But as the trajectory gets longer, that zero point 0.6 multiplier compounds, automatically de-emphasizing the late high-shift steps.
So it puts less pressure on the later steps.
Significantly less training mass on step 12 or 15 because the teacher's state space there is just too alien to the student's capabilities. If we connect this to the bigger picture, REPD isn't just about making things on policy, it's about dynamically balancing student relevance against teacher reliability.
That is such an elegant workaround. They don't force the student to overfit on the deep, highly complex parts of the teacher's history because it's essentially irrelevant to the student's current baseline. They just balance it by tweaking how much weight those later steps carry.
Yeah, they accept that the offline pool is a compromise, and they optimize exactly where in the timeline that compromise is mathematically most effective.
The theory is incredibly sound, but the real test is how this architecture performs in practice. Like when you actually bench this against live online training, what do the numbers look like?
The data reveals some fascinating plot twists, honestly. The researchers tested ROPD using the Qwen3 family of models. They took a 4 billion parameter student model and tested it with 4 billion, 8 billion, and 30 billion parameter teacher models.
Okay, pretty standard spread.
Yeah, and the results ended up cleanly dividing into two very distinct regimes of AI training.
So if the first regime is a straightforward task, how does offline replay hold up?
They tested this straightforward regime using a search environment, having the agent actively browse Wikipedia, query pages, and synthesize answers. In this scenario, the teacher and the student are already pretty close in capability.
The gap is small.
Right, which means the teacher's historical paths are already highly relevant to the student all the way through.
And the performance.
It was a statistical tie. Standard online OPD scored a 40.6% average accuracy, and the offline RIOPD scored 40.5%.
A tie is actually a massive victory here. You're getting the exact same performance, but RAIOPD did it in 7 seconds per step instead of 64 seconds with zero server infrastructure for live tool calls. That's a huge win for efficiency.
It really is.
But what about the second regime?
The second regime is where the gap between the teacher and student is wide. They tested this using complex mathematical reasoning, where the agent has to write Python scripts to solve intricate math problems. This is an incredibly deep, high-variance state space.
They tested this on AME24, right? Which, if you track these benchmarks, requires deep, multi-step logical deduction, making it the perfect stress test for that prefix trap we were talking about earlier.
Exactly the right benchmark for this. And when they used an 8 billion parameter teacher to train the 4 billion parameter student on these math problems, ROPD didn't just tie online OPD, it significantly outperformed it.
Wait, really?
Yes. On AME24, the live online OPD scored 28.3%. ReOPD jumped all the way up to 36.7%.
Hold on. A purely offline replay was almost 30% better than letting the student interact with a live environment. How is that even possible?
It all comes back to the prefix trap destroying the live training. In the live online OPD, the math problems were so complex that the 4B student was constantly driving the car into the ditch.
And the teacher was giving bad advice.
Exactly. The 8B teacher was constantly being queried in hallucinated, out-of-distribution states and giving bad, unreliable grading signals. RIOPD kept the student safely anchored to the teacher's reliable, successful historical paths.
Ah. And they used that kappa decay to focus the learning heavily on the early steps, where the student could actually bridge the cognitive gap.
It actively protected the teacher's grading mechanism from the student's chaos.
That is wild. By restricting the student to the teacher's recorded history, it actually learned to reason better than when it was allowed to roam free and experiment. And if you are doing all of this offline, this also solves one of the biggest infrastructure headaches for generalist agents, right?
Oh, you mean the multi-environment routing problem?
Right. Normally, if you want to train a single agent to do math and search the web, you have to spin up both live environments simultaneously. You have Python execution servers running, you have Wikipedia search servers running, and you have to route the agent dynamically between them during the training loop.
It's a networking and compute nightmare.
But with RIOPD, you don't need to route anything.
You bypass the live infrastructure entirely. You can run RL on a math teacher on Monday and save the text logs. You run RL on a search teacher on Tuesday and save the logs. You dump all of those trajectories into one unified offline text pool. And on Wednesday, you train your generalist student agent on everything at once.
Wow, so no live servers, no dynamic routing, just pure batch data processing.
Exactly. It fundamentally changes the economics of training capable agents.
Hmm.
But you mentioned they tested a 30 billion parameter teacher earlier. Actually, the paper highlights a paradox when they pushed it to a 32 billion parameter model.
Oh, right. So what does this all mean? You're telling me that giving a student a smarter textbook actually makes them learn worse if the teacher grading the test hasn't read that specific book.
This is perhaps the most counterintuitive finding in the entire study, and it challenges a core assumption most of us have about knowledge distillation. We naturally assume that a smarter teacher makes for a smarter student.
Yeah, I mean, if you want to learn physics, you'd rather have the data from Einstein than a high school teacher.
Right. So they took the historical recordings from a massive 32 billion parameter model and used those prefixes to teach the little 4 billion parameter student.
And what happened?
The student's performance actively degraded. It performed worse than when it was taught by the 8 billion parameter model.
How does giving a student a highly advanced, more accurate set of historical actions actually make them learn worse?
It comes down to the surrogate mismatch. A 32B model takes reasoning steps that are so advanced and utilizes tools in such complex, multi-layered ways that the resulting history is completely alien to a 4B student, even on step 1 or 2.
The gap is just too big.
The gap is unbridgeable. The 4B student looks at the 32B prefix and essentially says, I have no statistical intuition for how you arrived at this state, so your dense probabilities on what to do next are meaningless to my current weights.
It's like dropping a first grader into a graduate-level calculus class and asking them to predict the next variable in an equation. They aren't going to learn anything about math. Their gradients are just going to update into pure noise.
The paper empirically proves that the most important metric for prefix selection isn't the raw, standalone capability of the teacher model generating the logs. It's reliability and proximity.
That is fascinating.
The offline training data has to be close enough to the student's own natural distribution for the statistical learning to actually take hold.
That completely flips how we should think about curating training data for these small, highly capable edge models. So if we step back and distill the core value of this ROPD paper for the listener today, what is the ultimate takeaway?
I'd say the takeaway is that we can achieve high-end agentic capabilities without the massive compute tax of live environments. RioPD proves that by perfectly recycling the historical logs generated during standard reinforcement learning, we can get the dense, high-quality grading signal of knowledge distillation combined with the relevance of on-policy learning.
Doing more with less,
Right.
essentially.
Exactly. We are dramatically reducing compute time, cutting training steps from minutes down to seconds, and in complex reasoning environments, we are actually building smarter, more resilient agents by keeping them anchored to reliable paths.
It's a massive win for efficiency. But digging into this methodology leaves me with a final, slightly provocative thought for you to ponder. If RioPD proves that we can perfectly recycle the historical successes and failures of teacher models without ever needing a live environment to generate new ground truth, what happens down the road?
That's a good question.
As we scale this up, do we eventually reach a point where we stop simulating live environments entirely because it's just too expensive? Will the AI students of tomorrow be forced to learn exclusively from the historical offline simulations of the AIs of today?
It's definitely a risk.
It really raises the question of whether we are unintentionally creating a closed loop of recycled digital history, where future models only know how to act based on the recorded, decaying echoes of past architectures.
It's a fascinating technical frontier, and honestly, considering the sheer cost of live compute, it's a reality the community will have to address as offline pools become the standard.
Definitely something to mull over if you're building in this space. Thank you for joining us on this deep dive into ROPD. Keep questioning the architecture around you, and we'll catch you on the next deep dive.